let me give you guys a second to get in. I want to try something out as well. Click, click, click. I'm going to be testing a new mic with you guys, so I want you to tell me if it's going to work. So let me just set it up real quick. Audio input capture. Let's find out. Okay. Alrighty, can you all hear me if I am talking like this? Can someone just type in the chat if you can hear me or not? Echoey, huh? Okay. What if I do this? Is this any better? Oh, I see. Okay, how about now? That should fix it. Is this any better? Blah, 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 blah. Much better? Okay. Or better or much, well, whatever. Okay, cool. So, hooray. Yay. New mics are always fun. Okay, so hopefully this should also cut out some of the, like, whooshing noise that this poor laptop makes while trying to stream. So, cool. Okay. That being the case, let's go to it. More quantum today. More quantum mechanics. So yesterday, just to kind of recap what we did, we talked about, what did we talk about? Light, mostly. We talked about how wavelength of light and energy are related, and frequency as well. We talked about the hydrogen atom, and how we were able to calculate electrons being excited to different levels, how much energy was associated with those transitions. We were able to calculate wavelengths of light that would be absorbed or emitted by that hydrogen atom. And yeah, it was exciting and fun. So today we're going to kind of go into more real life stuff. Well, as real life as quantum mechanics can get. So we talked about light yesterday. And we know that light is a wave, right? We're going to learn that electrons have wave properties as well. They're definitely particles because we can, they have mass. They're components of matter, right? They have mass and they take up space. However, they often behave like waves. And so what that means is they've done experiments using electrons, using certain radioactive things or processes or photoelectric effect. You can kind of generate an electron flow, essentially. And they're able to demonstrate that. So there are certain things that light will do when light waves interact with each other. They'll kind of cancel each other out. Or they'll build upon each other and make themselves stronger. It's called interference. You'll learn about it in physics. And so it turns out electrons do the same things. And so they determine that electrons have wave-like properties as well as particle-like properties. And so this lovely scientist named de Broglie had come up with the idea that, well, hey, we can actually calculate the wavelength of a particle, which is an interesting idea. And that is going to be Planck's constant over the momentum of the object. MV is momentum. And that is mass times velocity. Alrighty, and so we can calculate for an electron that's moving at a certain speed, we could figure out what its wavelength would be. Again, I do not have these numbers memorized. I have our book here, though. Okay, it turns out that electrons in hydrogen move at about... I have this written somewhere. Aha! 6 times 10 to the 6, we'll say. So not quite the speed of light, but pretty close. And an electron's mass is 9.11 times 10 to the negative 31 kilograms. One more thing to note is a joule is equal to a kilogram times meters squared per second squared. Just so we know. And so if we look at this particular electron moving around inside a hydrogen atom, we can figure out what its wavelength is going to be. Again, by using that idea of this de Broglie wavelength. And so, since we have this, remember Planck's constant. And remember it's joules times seconds, but I'm going to go ahead and change those units for us. I've just done joule times second. I've replaced joule with kilogram meter squared per second squared. Over the mass, which was 9.11 times 10 to the negative 31 kilograms. And its velocity, which we're going to say is 6 times 10 to the 6th meters per second. And so let's look. Kilograms cancel out. We have one of the meters canceling out. Per second divided by per second cancels out. So we're going to be left with meters, right? So Kevin can go ahead and calculate this for us. Or whoever wants to. Of course, it's not limited to Kevin. But we're going to see that this can be done for any particle. It does not have to be an electron. And in fact, so what we're going to do next is we're going to calculate my wavelength. So as your chemistry instructor, we're going to see what wavelength I have. And we're going to see that for most matter of substantial mass, it's an interesting way of saying it, substantial mass will have incredibly small wavelengths. So let's go ahead and have a look. So, but first let's do this one. So something that's actually going to be relevant to us in quantum mechanics. Wait a second, is Kevin here today? Yes, he is. Okay. Which one of you is going to beat Kevin to the answer? That's the real question. Oh, Kevin wins. Okay. Okay, and so this one would probably be about an X-ray or so. And guess what? If you ever take analytical chemistry or spectroscopy or microscopy or something, you're going to see electron microscopes often use electrons as their light source of about this wavelength. So we're looking pretty small there. This is typically going to be about an X-ray level of electron. You wouldn't need to know that, but it's pretty short wavelength, which means pretty high energy, right? So this particular electron has the energy of roughly an X-ray of light. So fun stuff. Let's calculate my wavelength. So let's say that I weigh 6 67 kilograms. That's probably about right. And I move at a speed of 1.5 meters per second. So I am a heavy, slow-moving object. Let's go ahead and see what my wavelength is going to be. And so, same idea. H over mv. I mean, you can already see without having to calculate this, we have this crazy small number up top with an exponent of -34. So we're going to see my wavelength is going to be somewhere around that magnitude. Let's have a look. Let's see if I can beat Kevin today. So, with this, I get 6.59 times 10 to the -36 meters. Tiny. Tiny, 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 tiny. And so this is kind of useless. There's really no point in having a wavelength so small. It would never be noticeable. I would not be able to do anything with my wavelength. But it's fun to practice calculating it for no reason. Okay, so we're going to see that this momentum thing is going to be important because when things are moving so fast and they're so small, we're going to have a bit of uncertainty in our measurements. And so we're going to now talk about the Heisenberg uncertainty principle. So this is where your good friend Walter White got his nickname from on Breaking Bad after the scientist Werner Heisenberg. And he was able to calculate that the change in position and the change in momentum for something is always going to be equal to, or rather, it has to be greater or equal to h over 4 pi. This mathematics. So, this is the position. This is the momentum. So position, of course, where something is. Momentum is related to how fast it's going. And so, let's see. We can go ahead and try and figure this out. If we want to know where an electron is in a particular atom, that would be the same as saying this, right? If I just move mv to the other side of the equation. Let me look up the m and v again. So let's say that this time we still have the same what was it, -31. Our electron is still the same mass, right? And this time it's going at, we'll say this electron is going a little bit slower. Alrighty, and so the delta, of course, not going to be necessary since technically it's m delta v, and delta v is always already a change in, so we'll just make it mv. We'll make it a little easier on ourselves. So the change in x that we can identify, we're looking at right now. We're going to look at if we can find out where an electron is in a particular atom. So we're looking at its position, which is x. This is not something that we're going to need to calculate I'm just doing this so we can show why the Bohr model is not so good. But also, who doesn't like to have crazy calculations? Four pi times mass times velocity. And thankfully, I already have the answer here. Okay, so this tells us that we can know where an electron is within about 1 nanometer. So this just tells us so we can figure out where an electron is within about a nanometer. However, a hydrogen atom has a radius or a diameter of 0.1 nanometers. So, if we can only kind of figure out where an electron is within 1 nanometer, and we have an atom that is a diameter of 0.1 nanometers, we really have no freaking clue where electrons are. It's somewhere in the atom. Hooray. And so, we have no idea where the electron is. All this math only to show we have no clue where the electron is. Again, this is not something you're going to need to do any more calculations for. This is the idea, is that the uncertainty is higher than the actual diameter of the atom. And so we have no clue where the electron is within the atom. So that tells us that, so Bohr's model, remember the electrons were in orbits? That was like, here's our nucleus, here's some electrons floating around it, whatever. No good. Since we have no clue where the electrons are, these fixed orbits are not really useful to us, because saying that electrons are in fixed orbits, but then also saying we have no idea where these orbits are, it's kind of useless. So while it's a nice model for kind of an elementary understanding of atoms, it is not useful for us anymore. And so we have a new and improved model. And this has probability distributions. So if we accept the fact that we don't quite know where the electron is, mathematically, which thankfully we are not going to have to do, quantum physicists and quantum chemists have figured out that there are probabilities of where an electron will be. So while we don't know exactly where it is, we have a likelihood of where it is. And these are going to be what are called orbitals. So in the Bohr model, with those lovely, nice little orbits, these are orbitals. And we're going to see that there are going to be, we have a fancy number to describe the orbitals. And we call that the L, which is the magnetic quantum number. Or was that ML is magnetic? I'll try and remember. And we see that L can be from 0 to n minus 1 for a particular shell of the atom. So we still have this idea that we have the principal quantum number, which tells us the kind of level of the atom that we're on. And we're going to have what are called units of L, not units, numbers, principal quantum numbers of L, which describe the orbital that something is going to be in. And different orbitals have different shapes. And so we have some fancy letters to describe these. While principal quantum number technically goes to infinity, we really don't ever go above 4. Just not something we do. We could we go up to 7. We don't usually go beyond that, but it does exist. We could potentially go beyond that. We have fancy names for these orbitals based on these quantum numbers, which are based on what scientists thought their spectra looked like. So the letters are kind of arbitrary for our purposes. And we're going to see that an s orbital looks kind of like a sphere. A p orbital looks like a dumbbell. A d orbital has this kind of four-leaf clover thing going on, and f orbitals have 6 of these things. So this is just kind of the shape of the probability distribution. So for an s orbital, it's a sphere. So the electron is somewhere whizzing around within a sphere. For a p orbital, it's kind of got these lobes on them, where we will only find electrons kind of in these shaded areas. It's the same with all these. These guys should be shaded in as well. And so electrons typically stay in these shapes. And again, these are mathematically calculated shapes. We don't need to worry about calculating them. They've already done the math for us. But we're going to be able to describe electrons using quantum numbers. And we're going to be able to describe them using orbitals as well. And we're going to see different electrons in different orbitals behave differently. How exciting. Any questions so far? By the way. So basically the whole point of everything we've done so far is to show you that the Bohr model is bad. Not bad, but not quite right. So we've spent 20 minutes going on about why that model is not the best. Alrighty. We have another quantum number, which is ebb sum L, which ranges from negative L to positive L, including 0. And this just describes which way, how the orbital is oriented. And so, if we have an L of 1, we can have ML of negative 1, 0, and 1. Again, these numbers are just going to be ways we can very easily talk about where electrons are. And so we'll talk about these in a little bit. So it turns out that one of these corresponds to a p orbital that is going straight up and down. We have another one that is now horizontal, and the other one is kind of at a diagonal. We call these, I guess I should have done X first. We have 3 axes, right? I guess this first one is PZ. Who cares? It's just all a matter of perspective, right? And these are just kind of like if you have an XYZ axis or coordinate plane, just like which way they're facing. So the Y orbital in this case is just straight up and down. X orbital is horizontal, and the Z orbital is kind of going in and out. So just to describe which orientation that orbital happens to be in. For L equals 2, we can have MLs of -2, -1, 0, 1, and 2. 4 of these are going to look like this one, just different orientations. So shifted that way, shifted whatever way. The last one is kind of cool. I like it. It is, you know what? Maybe the book has a better picture of it. Let's see. Do we have pictures of the orbitals in this book? Oh, here are our d orbitals. Much better pictures than I could draw. So there is that funny looking one at the end. So it's just different shapes that these probabilities will have. And so that's a cool one, I think. Okay. Enough of these crazy numbers for now. F orbitals are even more crazy. They're fun. So for us, I'll give you the names of these orbitals. You don't need to memorize them. And this cool one here is... wait, what is the last one called? Oh, no. These are not the right names. XY. Oh my gosh. YZ, XZ, and then this is Z squared. Yeah, that's right. Who cares about the names? Not important to us. However, what this tells us is that we have, for a given we have 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. That's the important part again here. And so we're going to see that we're going to be able to describe electrons not only using these quantum numbers, but also by these orbitals. I know it's going to sound just crazy. Don't worry, we're going somewhere. Trust me. All this work for something that is seemingly simple. So, however, there's always a however, right? It turns out we only have half as many orbitals as we need. And so this ended up being expressed as the fact that we are going to have 2 electrons per orbital. And so we're going to see that we're going to have one more quantum number, which is going to be either positive half or negative half. And this just describes which way the electron is spinning. So electrons are just twisting around, right? And we're going to see that if we have two electrons in the same orbital, they're going to be spinning in opposite directions. So they're going to spin in opposite directions. And so that's the last thing we need to keep in mind here. So let's work with this now. Alrighty, here we go. We're gonna now start talking about how to use these quantum numbers. So remember that electrons always they want the lowest energy possible. And so we're going to see that the lower orbitals those are the small quantum number ones are preferred. Yikes. Okay, let's take a look. Let's take a look at lithium. Okay, we're going to start off with a fairly simple atom. And I will show you a very good shortcut. It's going to make your lives so much easier. But I have to show you this first. So, lithium has a whole bunch of possible potential principal quantum numbers. However, we see it's in period 2 on the periodic table, so we're probably only going to go up to n equals 2. The others will be for higher energy states. So we're not going to need to go past n equals 1. If we think about L, ML, and MS, let me make that a little bit smaller. Remember, L can go from 0 to n minus 1. Remember, this goes from 0 to n minus 1. So n minus 1 is 0, so this could go from 0 to 0, which means L has to be 0. For this case. Exciting, I know. Who's calling me? Go away. ML can be from negative L to positive L. So 0 to 0. And we know that we can have two possibilities for MS. We have two possibilities here. And so we're going to see that we can describe this by describing a box that uses N and L as its, and technically, we're not going to worry about ML right now. Let's just make this easy. We typically call this 1s. This refers to N. This one refers to L. We do not have MLs. That's saying we don't have any more orbitals that fall under this 1s category. And we're going to see that we could have two electrons in here. We could have one electron with a positive 1/2 spin, and the other one will be a negative 1/2 spin. We usually describe these as arrows going either up or down. So remember, two electrons, and we call them anti-parallel. Which means one has a positive spin and the other has a negative spin. By the way, the positive and negative, so when electrons spin, they create a magnetic field. When you apply a magnetic field to these things, they'll interact differently. So that's what you need to know. Actually, you don't even need to know that. Just suffice it to say they spin the opposite directions. Yikes. Let's take a look at our second one. We have, for n equals 2, we have 2 potential L's. The MLs, we have 3 of those. And of course, MS is always just positive or negative half. I know, totally crazy. But again, I'll show you how to do this a lot more easily in a little bit. But for whatever reason, we like to describe it this way. So this tells us we have go away. We have a 2s orbital now. Remember, n is going to be our first number there, and L is those letters. So an L of 0 is S, and therefore that L will have no MLs. It will just be 0 as well. However, we have an ML of -1, 0, and positive 1. I know, I probably seem like I'm rambling with all these like random numbers and stuff. Trust me, there's a point. We're going to put in an electron. And lo and behold, remember this was lithium, right? Lithium has 3 electrons. Oof. So, we're going to fill them in this manner. We're going to put 2 of them in the lowest energy orbital. And then we're going to put our last electron in the next lowest energy orbital. All this work, all these numbers for nothing. What this is going to show us is that we fill 1s, then we fill 2s, then we fill the 2p orbitals, then we fill the 3s orbitals, then the 3p orbitals, etc. We're going to go crazy. This is the lowest energy and the highest energy. One more thing is that we have to remember how many of each orbital we have. For p orbitals, we actually have 3 of them, right? And it's going to be the same for no matter what your principal quantum number is. There are 3 p orbitals. Where are we? I told you I'm not going crazy. This stuff does eventually lead somewhere. Besides going around in circles forever and crazy numbers. What we have to understand, one more thing, is that we always fill lowest first. This is what's called Hund's rule. And we always fill them singly before pairing. What this means is for something like nitrogen, let's look at nitrogen. It has 5 electrons. What's nitrogen's atomic number? Oh, it's 7, isn't it? Yeah, it's 7. We're going to want to fill those lowest first, and we fill them one at a time until we are full. So here's our 1s, 2s, 2p. If we go to the next one, we still have electrons left, so we're going to fill up our 2s orbital. The next one, we're going to want to do one at a time. We fill one at a time, and we do what's called parallel spin, which means the arrows are, yeah, exactly. They're going to want to be far from each other. So they're going to be in different orbitals until we can't do that anymore. And so that's what this is going to look like. So we might describe this by saying there's 2 electrons in the 1s orbital. There's 2 electrons in the 2s orbital. And there are 3 electrons in the 2p orbital. One thing to notice, or not notice, rather, one thing to learn is that these three, the 3 2p orbitals are degenerate. Fancy word. Tyler, I'll get to you in 1 second. And that means same energy. And so we're going to, since there's no difference in the p orbitals, we'll just fill them one at a time. Okay, how did we get 1s and 2s and all that stuff? Okay, so do you want the easy answer or the fancy answer? The answer you'll understand. Okay, this order is this is always the order we fill them. So however many electrons we have, it's always this order. Okay, that's the answer that you'll understand, presumably. So we always fill them this way. We fill them all till maximum capacity before we move to the next orbital. So so did that answer? I'll show you a much easier way to do this, but for whatever reason we liked. Oh, that didn't work. Okay. So I'm gonna just copy this down here. Okay, let's do nitrogen again. We have 7 electrons total in nitrogen. We always are going to fill the lowest energy ones first. This is how we're going to know. So this is the lowest here, and this is the highest of the ones I've written. Okay, so 1s, all s orbitals will just be one box, because s orbitals can only hold 2 electrons. We only have 1 s orbital, so they're only going to be able to hold 2 electrons. P orbitals, however, we have 3 of those, so those can hold up to 6. Okay, so if we start filling them, there are our first 2 electrons. So we had 7, we've just used 2, we got 5 left. We now start filling up our next one. we've used another 2. We have 3 electrons left. So we're going to put them like this. For oxygen, again, I'm going to show you an easier way to do all this stuff. For oxygen, we have 8 electrons. Following the same idea, we always want to fill them separately first in your p. Let me make that p orbit a little bit bigger. So we're going to fill it like this. So we're going to fill them singly first, and then we are going to start pairing them off afterwards. And we understand that 2p is lower energy than 3s. It's going to be closer to the nucleus, so that's going to be a happier situation. You can think of these as kind of like hotel rooms, or maybe like seats at a concert. So understanding that like 1s is right up close to the performer, and then 2s is behind that. And those seating areas have seating limits, right? You can only hold so many people per area. And so, like, if you think about it as like a concert venue, here's Tyler singing for us. This is our 1s seating area. That's our 2s area. And here are our 3 2p areas. And so if, whoever's going to see Tyler sing, or do whatever performance, if all these cost the same, of course people are going to buy the closest seats possible, right? If price is no object, until they're filled up. And so that's the same idea here, is that we're going to fill up the closest ones first. So there, now that one's full. And of course, humans, we don't like each other, right? We have to be socially distant. So we're going to fill separately first. And we say, hey, wait, nobody's in the right box, let's go there. But now, if we take a look, they all have the same number of people. There's 1 seat left in all of the 2Ps. So whatever, I'll go and buy my ticket here instead. So that's the idea of doing this. So essentially this stuff is just like how close you are to the nucleus. Electrons like to be close to the nucleus. It makes them low energy. The farther out you get, the bad it gets bad. Yeah, this is a lot easier, right, if I explain it this way. But quantum mechanics, it's exciting. By the way, if we look at these 2 electrons, we're able to calculate their, or we're able to figure out what their quantum numbers are. We see that these guys are in the same orbital, so they will have the same first 3 numbers. So you may be asked to say, like, here's a bunch of quantum numbers, figure out where this electron is, or something. This is how you would relate it. Remembering that the L quantum number, n just goes from 1 to infinity. We'll just say 1 through 7, but it really goes to infinity. Remembering that L goes from 0 to n minus 1, and that an L of 0, 1, 2, or 3 means an s, p, d, or f orbital. The MLs tell us how many orbitals. And that goes from negative L to positive L. So that tells us for an s orbital, we just have s, we have 3 P's, 4 D's. Does it, or 5 D's? They don't matter which D's. And you have 7 F's, which I'm not going to draw. And then, again, MS can be positive or negative. So, if we are looking at a random electron, let's say again, this sort of stuff is not going to be useful to us unless we're doing crazy stuff with electrons. But it is part of the curriculum, so I have to teach it to you. N of 3 tells us that it's in the third shell. L of 1, if we look at our chart, means it's a p orbital. So this information together tells us it's a 3p orbital. And so if we understand that the ml of a p orbital just looks like this, just ways of describing which orbitals it's in. The positive 1/2 is usually this arrow up here. So if we have, let's say we have an element that has a cajillion electrons. Okay, random element here. These numbers mean we are talking about this electron right here. These two numbers have told us it's in the 3p orbital. The ml of -1 has told us it's kind of in that first box. And the ms equals 1/2 means it's just the one that's pointing up. The positive one. That's it. So I could give you an electron configuration like this and say, okay, what are the quantum numbers for this one? In fact, let's do that. Oh no. What have I done? Yikes. Let's find the quantum numbers for that green electron. So we have 4 quantum numbers that we're going to need to find out. Oops, not m1/2, ms. Oh my gosh, we have been Twitch bombed. Yes. That is our second one. Do I want to become famous? Yes, I do. All right. Go ahead. Don't go there, by the way. All right. So, let us look at our green electron here. The easiest one for us to do is N. N is the easy one. What is the N for the green electron? Yeah, N is 2, right? Because it's 2p is where it is, right? So remember, N is the first number. So for L, we have to go back up to our list here. we have L of 0, 1, 2, or 3, and that tells us the letter of the orbital. So if this is in a p orbital, that means that L is going to be what? Yeah, right, exactly. L is 1. And so remembering that the MLs just kind of go in ascending order, this L or this ML is going to be which one? If we look up here, we have a one that's written out for us. Zero, right. Alrighty, and then the electron is pointing down, which means our spin is going to be negative. Exactly. And so all this crazy work we're able to figure out, and you go into crazy physics, and poof, there you go. You can learn about why using these might be useful for you. But for us, it's just ways of talking about identifying electrons. Big thing here. No two electrons can have the same quantum numbers. So that makes it, using these 4 numbers, we're able to pinpoint exactly which electron we're talking about. And so in this case, we're looking at one that's in the 2py orbital that's spinning down. And so if we wanted to look at exactly one electron, we would describe it, we would identify it using these numbers. And so this is what's called the Pauli exclusion principle. And believe it or not, this principle actually is the reason like everything can exist. Like without this one, it turns out like all hell would break loose. Since we're mostly empty space, right? Most of our atoms are empty. Yeah, right? So if this didn't exist, we would just like fall through the floor. Because if our electrons could occupy the same place at the same time, there would be no repulsion from each other. And so everything would just fall through each other. And so, yeah, it's a big thing. So Pauli exclusion. Okay. Back to configurations. Let's find a shortcut. I guess I have to go all the way down. Oh, experiment. Oh, you want to see if we can violate the Pauli exclusion principle? All right, go ahead, design an experiment for it. We'll have fun. So this is the periodic table with those kind of 2 rows stuck in. Sometimes we take the 2 rows at the bottom and just we snip them out just to make it not so big. Anyways, we're going to be able to see that we can kind of classify sections of this periodic table. We call this the S block, the F block, the D block, and the P block. And so we're actually going to be able to figure out the electron configuration of a particular atom just by looking at where it is on the periodic table. These blocks tell us in which orbital the highest energy electron is. So what this means, let me add one more thing. The columns tell us how many electrons are in that orbital. What this means is if we look at fluorine over here, small fluorine here, why did I even put a box? Fluorine right here. Fluorine is in the P block. Hopefully there is no confusion on that. Right side of the periodic table, P block.
I don't know that one.
No, go away, Alexa. Okay, looking at this, there are 6 columns in the P block. Do I have a periodic table here? Oh, duh, of course I do. Aha! Let me write on this. Yes, screen right. Look. Let's not use red. Let's use blue. Fluorine is right here. Yes? This is the P block. Again, F is the stuff at the bottom that's like not even here. In the one that I drew on our notes, I've included those, but typically the F block is just left at the bottom. Anyways, we have 6 columns within the P block. We also have rows of the periodic table, right? Where fluorine's position tells us is that fluorine is 2p5. How on earth did I get that? This is going to tell us what the highest energy electrons are. So that's going to be the end of where fluorine's electrons are. And I got that. Notice, here's the 2. Here's the 5. And there's where I got P from. It's the P block. Is that okay with everyone? Does everybody see how I got 2p5? Alrighty. So, let's go back to our notes. If fluorine ends with 2p5, that tells us, remember, that that's the highest energy ones, which means all lower orbitals are full. Because we know the highest energy is 2p5, so everything else has already been filled up. And so, if I just kind of do our little cheat sheet here, I'm going to show you how to do this where you will not need the cheat sheet anymore. This tells us that because 2p is our highest energy, that these are the full ones. And so we know that s orbitals can hold 2 electrons. So the electron configuration for fluorine is poof, there. Done for us. It has 2 electrons in the 1s orbital, it has 2 electrons in the 2s orbital, and it has 5 electrons in the 2p orbital. And if we were to draw the boxes for this, we could do that. We know we have 2 electrons in each of those. We've got 5 electrons there. We can double check. It looks like we have 2 plus 2 plus 5 electrons. That's 9 electrons total. Lo and behold, fluorine has an atomic number of 9, showing us that we are indeed correct. This is our electron configuration for fluorine. So, going back to the periodic table, oops, I don't need krypton, go, or xenon, go away. Oh my gosh, we're so out of time. Why did nobody tell me? Well, fine, I'll just finish this thing. You guys are so excited about chemistry, huh? Why can't I write on this right now? Let me write on you, silly thing. There we go. Okay. No, I don't know what this thing is. Okay, cool. So, let's write on this. So, oh no, it cut off hydrogen. How silly. Okay, you know what? Forget it. We're going to do this in the notes real quick. I'm ignoring the F block. Sue me. Okay, here's our periodic table. Boom, we're going to do this real fast. Fluorine, right here. We have found that it is 2p5. We have to fill in everything that comes before fluorine, essentially, on the periodic table. So that tells us we have to go from 1s. Helium is also 1s. It's a separate one. Then we fill 2s. Then we fill 2p up until f. And so we're going to fill in 1s. We're going to fill in 2s. And then we're going to end at 2p5. If we were looking at chlorine, chlorine ends with 3p5. We would also have to fill in everything before chlorine. So that would be 1s2, 2s2. Then we go to 2p. We have to fill it up all the way. For chlorine, we're continuing to go. Then we go to 3s2, and then to 3p5. So we're just filling in everything else completely. And so we can use the periodic table to have us understand the energies of these orbitals. Okay, I realize I'm totally out of time. Sorry for keeping you guys late. This stuff is not on your exam, so go ahead and drain it out of your brain so that you can panic for it for exam 3, which will be, I think, in 3 weeks or something. We'll continue this on Tuesday. Couple last things here. Tomorrow is a review session, so bring questions for me. I'm tempted to start at 10 o'clock instead. Would that be okay with you guys? You know what? No, never mind. Let's keep it at 10:15. So I'll see you guys 10:15 tomorrow with questions. Your homework is due Saturday at midnight. Have I posted homework for this stuff yet for you guys? I don't think I have. Or if I have, it's due next week. So not Sunday. It's due the following Sunday. If I haven't posted that yet. Okay. So those are the announcements. Yeah, good stuff. Okay. I will see you guys tomorrow if you want. No new material tomorrow. Okay, take care.